All right, welcome to my channel, guys. Just kidding. Welcome to Unit 6 Test Review, hosted by yours truly, Miss O. Okay, so let's get started with the 6.3 transformations and key features. All right, so when we're talking about transformations and key features, we're talking about the transformations that happen given this formula right here, where if it's negative in front, that means there's a reflection. If the A is greater than 1, it's a stretch. Less than 1 is compression. H goes left and right, but remember X lies. And K goes up and down. Sorry. Okay, so moving right into it, first off, we have this graph here, the graph of 1/2 times the square root of x plus 3 minus 5. Now, our square root function's parent graph are 0, 0, 1, 1, 4, 2, and 9, 3. Now, the transformation, starting with the first thing I see here, this 1/2, when the a value is less than 1, I guess I can write that up here. When the a value is less than 1, we have a um, vertical compression. All right, and then this number here is h, and remember x lies, so h is really -3. And our last number here on the outside of the radical is k, and k is exactly what she says she is. So that -3 tells me we are moving right, oh, just kidding, left, left 3, and down 5. So once you get your transformations, we can plot the parent function 0, 0, 1, 1, 4, 2, and 9, 3. This is the parent. Now our graph for the vertical compression, we can do this two ways. I showed you guys both ways. The first way is to use a highlighter to graph the A changes, the changes in A. So we have a vertical compression by 1/2, so we're taking all of the Y values that are already on the graph and multiplying them by 1/2. So first we have 0 times 1/2, which is 0. 1 times 1/2 is 1/2. 2 times 1/2 is 1, and 3 times 1/2 is 1.5. All right, now we're going to take all these points and move them left 3 and down 5. So 1, 2, 3, 1, 2, 3, 4, 5. This one, 1, 2, 3, 3, 4, 5. Okay, 3, 3, 5. 3, oh, did I move the wrong one? I think I did. Yellow one. 3, 3, 5. 3, 3. Did I do something wrong? 3, 3, 4, 5. 3, oh, 3, 1, 2, 3, 4, 5. That's where it is. Okay, I messed up just a tiny bit. Next, this 3, 3, 4, 5, and 3. It's in the half. So 3, 1, 2, 3, 4, 5. All right, I moved left and down 5. This is our new graph. Okay. The other way to do that, let me rewrite this parent function graph. So the other way to do that is to start a table of x and y. And to the x, we will add or subtract the real value of h. Y gets multiplied by a, and we add or subtract k. So in this case, our original function points were 0, 1, 4, 9. And the y values were 0, 1, 2, 3. Okay, so our h is -3, so we're going to subtract 3 from each of these. 0 minus 3 is -3. 1 minus 3 is -2. We got 1 and 8, 6. All right, this last one. Now our a value is 1/2, so we're multiplying everything by 1/2. And it says down 5, so -5. Okay, so half of 0 is 0, -5 is -5. Then we got half of 1 is 1, -5, or sorry, half of 1 is 1/2, -5 is -4.5. Half of 2 is 1, 1 minus 5 is -4. And then this last one will be 3.5, negative. And look, there's our new points. -3, -5, -2, -4.5, 1, -4, 6, -3.5. So there's our new points of the new graph we just drew right here. All right, now the domain of our square root function. Domain represents the x values from left to right. So if I took my pencil and moved from left to right, what is the furthest left, or what is the lowest x value? Our smallest x value is right here at -3, and then our graph continues on towards positive infinity. All right, now the range are the y values from bottom to top. Now from the bottom, our lowest y value is -5, and as we go up, our graph is going to continue increasing towards positive infinity. Oops. So we have -5 to infinity. Now the vertex, remember, we don't even have to look at the graph to remember what our vertex is. Look, oh, can I ignore it? Can I put it away? No? Okay, look, I'm not looking at the graph at all. Okay, I am looking at the graph, but let's pretend I'm not looking at the graph. Let's pretend I can't see the vertex right there. And we can just remember that the vertex is HK. Remember, H comes right from our equation, and K also comes right from our equation. -3, -5. And oh, looky here, our vertex is at -3, -5. Oh my goodness. Something cool about the vertex that you might be recognizing right now is that the domain, the x value, starts the vertex, and our range, the y value, starts at the y value of the vertex. So that's cool. I like that. All right, let's move on. Number 2, graph the following function and identify the transformations and keywords. Whoop-de-doo. First things first, there's a negative here, and that negative tells me we are going to be reflecting over x-axis. Next here we have a 2, and that number is larger than 1, so we're having a vertical stretch. Right here, that's our h, and one moment. Okay, sorry guys, continuing on. The -1 is our h value. Let's try and keep consistent with these colors here. H, remember x lies, so h is actually +1. And the last one here is k, and k is 4. All right, so that h value of 1 tells me that we are moving right 1, and we are moving up 4. And let me just specify that the vertical stretch is by 2. Okay, so this is the cube root graph, and our cube root of x graph, the points are um, the points are 0. No, okay, I got this. -8, -2. So let me just graph it because then I can see exactly where it's at. Okay. -1, -1, 0, 0, 1, 1, and 8, 2. All right, so our parent function here, we graph it on the table, on the coordinate grid, I mean. Something like that. Sorry, my graph is not perfection. All right, now, again, two ways of doing this. We can graph the changes or use the table, which personally I like the table better, but I know you guys like the highlighters. So first things first, we need to highlight all of our points across the x-axis. We should all know how to do that. That's back from geometry and like middle school. So, all right, next we have a vertical stretch by 2. So all of my highlighted points, the y values need to be multiplied by 2. I'm just going to use a different highlighter. All right, so this first one is at 2. 2 times 2 is 4. All right, the 1. 1 times 2 is 2. 0 times 2 is 0. -1 times 2 is -2. And -2 times 2 is -4. All right, so the green one, I'm going to highlight so I know which one is which. Yellow was the reflection, green was the stretch. Now I'm going to take all the green ones and move them right 1 and up 4. So right 1, up 4, right 1, 2, 1. Okay, that one's. I hope you're doing it on your own too. All right. Oh, I did one dot too far over. No, that's correct. Okay. Here's our graph. The red one is our new graph. And the domain from left to right, -infinity to positive infinity. Zena, stop. Sorry about my dog. Range, bottom to top, -infinity to positive infinity. And the last one here, the vertex, remember H, K. So in this case, it's 1, 4. Or just the point where the graph changes place, which is in the middle there. Originally it was here, now it's here. All right, moving along. Oh, I forgot to do the other way. Okay, if we wanted to do the table, x plus 1, because that's the h, y is times 2, and plus 4. All right, so 8 plus 1 is, sorry, -8 plus 1 is -7. Now we have 0. Now we have 1, 2, and 9. All right, y, everything times 2 and plus 4. All right, -2 times 2 is -4, plus 4 is 0. 2 times -1 is -2, plus 4 is 2. Then we have 0 plus 4, which is 4. 2 plus 4 is 6, and 4 plus 4 is 8. And if you check, those are our new points of the graph in red. Okay? All right. So moving along, number 3. Write the equation of the transform function graph below. All right, so first things first, we should check out that vertex. Our vertex is here at 1, 2, which means that's my h and that's my k. Now, the original graph started at 0, 0. So our vertex has moved right 1 and up 2. So our entire graph is moving right 1 and up 2. Now, if I look at these other points, we have they haven't been stretched or shrunk at all. So here, this point is at 2, 3, and this is at 5, 4. Now, our original graph started here at 0, 0, 1, 1, 4, 2, and all of these points have moved up 2 and to the right 1, 2 to the right 1, up 2 to the right 1. So those are the only transformations that are happening here. So our equation, this is also the square root function. Square root starts at a point and goes out, and the cubed root goes like this. Actually, I think I did it upside down, but you get the picture. Hopefully. Okay, so I can draw this beautiful graph. Boom! There's our cubed root, and this is the square root. So very different graphs. So yes, no a value, square root of x minus 1, because remember x lies, and we went up 2, so plus 2. There's our graph. There's our equation. All right, so 6.4, inverse functions. All right, graph the following equation and its inverse. So when we solve these, it gives you the x values. We're going to plug these x values in for x and solve for y. So first we have 1 minus 3, which is negative 2, and negative 2 cubed is 8. All right, next we have 2 minus 3 cubed. 2 minus 3 is negative 1. Negative 1 cubed is negative 1. 3 minus 3 cubed. Well, 3 minus 3 is 0, and 0 to the anything is 0. 4 minus 3 cubed. Well, that's 1, and 1 cubed is 1. 5 minus 3 cubed. 2 cubed, 2, 8. All right, now the inverse, we swap them. Okay, now we can graph both the original function and the inverse. I'll do the original in green. So 1, 8, 2, negative 1, 3, 0, 5. What did I do wrong? No? Did I do anything wrong? Oh, that's a 3. 2 cubed is still 8. Negative 2 cubed. Ah! Negative 2 cubed is negative 8, so my mistake there. That first point needs to be at 1, negative 8, and that means this one over here needs a negative. 2, negative 1, 3, 0, 4, 1. All right, so there's our graph. This is the original f of x, and yes, we definitely need to label it. Now our inverse, negative 8, positive 1, negative 1, 2, 0, 3, 1, 4, and 8, 5. Negative of x. All right, cool. Now remember, this is the line y equals x, and all inverses are perfectly reflected across this line. So if this line is a mirror, the green graph is perfectly reflected across that mirror. All right, let's take a look at the next one. X plus 5 to the 1/2. Well, we know the 1/2 can be rewritten as the square root. So no longer 1/2. Now we have the square root of x plus 5. So let's go ahead and plug these numbers in. Negative 5 plus 5. Well, that's 0, and the square root of 0 is 0. Square root of negative 4 plus 5. Well, negative 4 plus 5 is 1, and the square root of 1 is 1. Square root of negative 1 plus 5. Well, negative 1 plus 5 is 4, and the square root of 4 is 2. Now we have the square root of 4 plus 5. 4 plus 5 is 9. Square root of 9 is 3. All right, now the inverse, 0, negative 5, 1, negative 4, 2, negative 1, 3, 4. All right, so let's go ahead and plot the original, which I'll do in green just to keep it consistent. -5, 0, -4, 1, -1, 2, 4, 3. Here's our original graph. Label it. And the new graph, 0, -5, 1, -4, 3, 4. Oh, I missed one. 2, -1. There we go. All right, and look, they are perfect inverses and perfect reflections across the line y equals x. Okay, great, and this is our inverse. All right, next page. Find the inverse of the function algebraically. All right, so when we solve for inverse algebraically, our first step is to change this as well. Change f of x to y. Step 2, swap x and y. Step 3, solve for y. And step 4, rewrite with inverse notation. Okay, so first step, let me zoom in. First step, change f of x to y. Next step, swap x and y. Now solve for y. We'll start by subtracting 3. And we can divide by 5. And then we can take the square root, or sorry, we can square both sides. Something I really tried to hammer down in my classes is that we are not just squaring the 3, we're not just squaring the x, and we're not just squaring the 5. We're squaring the entire right and left side. So be sure you put that whole left side in parentheses before you put that 2 there. All right, so now we have x minus 3 over 5 squared equals 5 minus 1. Last step is to add the 1 side, and that 1 is being given after with the parentheses there. So you need to make sure that 1 is outside the parentheses and not being added to anything inside. There we go. That's it. And it is that easy. All right, let's take a look at the next one, number 7. First step, change f of x to y. Next step, swap x and y. Then solve for y. So we start adding the 8. Then we can divide by 3. Next step is to cube both sides, the entire sides. Last step is to subtract 7 on the outside of the. Oh, we don't need equals back. That's it. 7. All right, there we go. Composition. All right, now we're going to take one function and put it inside the other. So we need to see which one is inside first. First, it's g of x. So I'm going to take this whole function and it's going to go inside here. Personally, I like to start by writing the inner function and then writing the outer function around it. So cubed root x plus 1 minus 7. There's our total, there's our whole g of x. And it's going right here. So what's after this x here? Well, we have a plus 7. Okay, I apologize for the dog barking. Hopefully your ears are not bleeding. Okay, so let's continue. We have the inside function g of x. Now, what's going to go right around this x that was here? Well, we have a plus 7. That's all in parentheses, being cubed, and then subtracting 1. And as you can see, that green function was our x, and now we have the plus 7, the cubed, and the minus 1 there. All right, so now to simplify this, remember when we're simplifying, we're following inverse operations, which means PEMDAS backwards. So we're starting with addition and subtract. Oh, just kidding. Oh my God, I'm getting ahead of myself. I'm so sorry, guys. So we're simplifying, so we're using regular order of operations starting with parentheses. So that means looking inside the parentheses here, is there anything we can cancel out? If you guessed the 7s, yeah, you're right. Now we have what's left. All right, so moving on from the P, now we go to E, exponents. Looking at our exponents, can we cancel out those exponents? Yeah, we have a cube and a cube root. Those cancel out. And our last cancellation are the ones, the addition and subtraction. Done. And we have simplified down to x. So are these inverses? Maybe. They might be. I did see a lot of people on their inverse worksheet, and I will have individual conversations with you. But on your inverse worksheet, a lot of you guys had only done one side, and then you were kind of like, oh, they're inverses. We do not know if they are inverses yet. You have to check both sides. So those of you that did not check both sides, well, you probably got a 50 on your worksheet. I said it a billion times in class. Okay, so are they inverses right now? Maybe. We don't know for sure yet. The other way has to simplify down to x as well. All right, so let's check it out. On this side, f of x is on the inside. So we're going to take this function and put it in place of x on the other function. All right, so I'm going to start by writing the inside function, set x plus 7 cubed minus 1. That's our inside, so put it all in parentheses. Now, this inside is going to go right here. So what's around that x? Well, we have a plus 1, a minus 7, and this cube root is only over the 1. It is not over the 7. All right, now, PEMDAS, looking at the inside of the parentheses, which really means the inside of that cube root there. The first thing we can cancel out are the 1s. That leaves us with the cube root of x plus 7 minus 7. Now we move on to exponents. Oh, sorry, I forgot the cube. Yeah, the cube root and the cube cancel out. And now we're left with x plus 7 minus 7. Now those 7s cancel out, and we are left with x. So now, are these inverses? Yes, they are most definitely inverses. Now on your test, you are going to have to explain whether they are inverses or not and why. So make sure you know this part. These are inverses because they both, keyword both, simplify to x. All right, one more composition. All right, inside is g of x. Here's our function. Let's copy it down. Square root of x minus 4 minus 5. Put the inside in parentheses. Now, outside of this x, on this f of x here, we have plus 4. That's in parentheses with a square and plus 5. Now again, PEMDAS, starting from the inside. Can we cancel anything out? We can't cancel anything out, but this 5 and 4 can be combined. So negative 5 plus 4, that's going to be negative 1. All right, now moving on to exponents. Well, we can't cancel out the root because this -1 is being squared as well as the square. So can't really do that there. So what it's looking like right now is that these are not inverses. This is not going to simplify down to x. Let's check the other side just for good measure. On this side, we have f of x in the middle. So we take f of x plus 4 squared plus 5, and it's going in place of that x there. All right, so again, starting from the inside, the only thing that can really be simplified here is combining the 5 minus 4. Well, 5 minus 4 is 1. And yeah, moving on to exponents, I can't cancel out the exponent 2 with the radical because the radical is covering over the 1. So we can't cancel that out there. The only time we can cancel out the radical with the 2 is when what is being square rooted, like for example over here, I'll draw you a picture. What is being square rooted is also being squared, or maybe like this. If we have x plus 1 plus 3, this is being squared and that whole thing is being rooted, this will not cancel out because the 3 needs the root still. So from here, we cannot go any further. These are not inverses because they don't simplify to x. All right, next problem. Solving, my favorite. All right. So first things first, well, let me just say two. We are following inverse order of operations when we solve. So we start with addition and subtraction. And really, there's no addition or subtraction that can be done here, no multiplication or division that can be done here. So we move right on to the exponents, where we need to get rid of that root, leaving us with 5x minus 1 equals 4 cubed. So 4 times 4 is 16. Times 4 is 16 and 16 is 32. 32 and 32 is 64. 1. 65 divided by 5. Is it 12? Let's check. 65 divided by 5. 13. I should have known that. It's all right. We're not perfect. All right, moving on to the next one. Again, starting with the cube root. We got to get rid of that root before we can touch anything inside. 2x minus 1 is 16 cubed. That's ugly. 16 times 16 times 16 is going to give us, is that serious? 4,096? 4096. That's crazy. Is that a typo? Well, we'll just go along because at this point we're already almost done, so who cares? 4,097 divided by 2. A little obnoxious. I promise you the test isn't like this. Divided by 2 is 2,048.5. All right, that was an ugly one. Okay, moving along. Solve the equation. Be sure to check for extraneous solutions. Okay, so here we have a 1/2 exponent, and when we have the 1/2 exponent, that can be rewritten as the square root. All right, first things first, let's get rid of that root by squaring both sides. And now we have negative 3x plus 4 x squared. Right now, you should be noticing that there is an x squared and an x. And when both are present in one equation, we know we're going to have a quadratic equation, which means we need to factor. So let's go ahead and move everything to the x squared. So minus 3x minus 4. Now we have 0 equals x squared minus 3x minus 4. All right, now we can label our A, B, and C. A is 1, B is -3, and C is -4. So our t-chart is going to have -4 at the top and -3 at the bottom. So our two factors, 1 and 4, and 2 and 2. Which of these have a difference of 3? 1 and 4. Which one needs to be negative for them to add up to a -3? +1, -4. All right, when we set these equal to 0 and solve for x, we get x equals 4 and x equals -1. You don't even have to solve for x. We could just remember that x lies and change the sign. All right, now that we have our two possible solutions, we are going to plug these into the original equation. I'm going to zoom out here so I can see it. So we have -3 times -1 plus 4. Let's go ahead and put that square root on there. Equals -1. The other one is 4. Oh, whoops. -3 times 4 plus 4 equals 4. All right, starting from the inside. -3 times -1 is 3, plus 4 is 7. Square root of 7. Is the square root of 7 equal to -1? No. That's a false answer. So this is false. Let's not write the false here. Let's write the false with the x equals. All right, next we have -3 times 4, which is -12, plus 4 is 16. And that square root of 16 is 4. So does 4 equal 4? Yes. X equals 4 is our true answer here. All right, moving on to the next one. Okay, first things first, we should get this 1 away from the square root. Now we'd have to square both sides to get rid of that radical. Now we have x plus 7 equals x plus 1 times x plus 1. Now we should FOIL that out. X times x is x squared. X times 1 is x. And then x times 1 and 1 times 1, 1. Now I'm starting to see that we have an x squared and some plain x's present. So again, quadratic equation, and we're needing to factor. Let's go ahead and find the terms on the right side. X and x can be put together to have 2x. Now let's go ahead and subtract everything over to the other side. 0 equals x squared plus x minus 6. All right, ABC, A is 1, B is 1, B is -6. T-chart, -6 on top, B value on the bottom, 1 and 6, 2 and 3. Now, which of these would add up to a 1? 2 and 3. They need to multiply to a -6, but add up to a +1. So -2, +3. 3 minus 2 is +1. We got x minus 2, x plus 3. X equals +2, x equals -3. Now we can take those numbers and plug them into our original equation to check. All right, original equation 2. So the square root of 2 plus 7 minus 1 equals 2. And the other one is -3 plus 7 minus 1 equals -3. All right, so starting from the inside, 2 plus 7, 7 is 9. Square root of 9 equals 2. Square root of 9 is 3. Minus 1 is 2. Yeah, 2 equals 2. So 2 is our true answer. We can assume the other one's wrong, but let's check it anyways. Negative 3 plus 7 is 4. 4 square root of 4 is 2. Minus 1 is negative 1. And does negative 1 equal negative 3? No. False. Answer. All right, we are almost done. 4 more questions. All right. Again, a little more solving. Here we have the 1/2 exponent, which can be rewritten as the square root. To get rid of the root, we need to square both sides. 2x minus 2 equals 4 times 4 is 16 plus 2 divided by 2. All right, next. 1/3 can be rewritten as the cube root. So we can subtract 4 and then take the cube of both sides. And if I'm moving too fast for you at any point, just slow down the video. On YouTube, you can change the pace. All right, so negative 3 cubed is negative 3 times negative 3 times negative 3. Negative 3 and negative 3 is 9 times negative 3 is negative 27. And as usual, your answer is totally fine as a fraction. All right, moving to the back. Last 2 questions. These last 2 are like applying what we've learned about solving to real world situations. So don't overthink this. Just write out the problem and solve it. Regular math. So a television screen is measured by the length of its diagonal. Did you know that? So if you have a TV and it says you have a 50-inch TV, it's not 50 inches this way or this way. It's 50 inches across the diagonal. Cool, right? All right, you learn something new every day. Anyways, the equation d equals the square root of 2a estimates the length of the diagonal d of a television screen with area a. John wants to buy a new large screen television that has 3 times the area. That already sounds like the A, right? Of his old screen, which was 294 square inches. Express area as a function of the distance d. So in plain people words, that means write an equation for area. So area, I don't have a key for this, so I'm doing this off the top of my head. Okay, the equation d equals the square root of 2a. The old screen was 294 square inches, and the new screen is 3 times the area of his old screen. So 3 times the area of his old screen, 294 inches. So if his old screen area was 294 and the new screen is 3 times the old area, that means the new area is 3 times 294. So 3 times 294 is 882. This is the new area. All right. And if this is our formula, d equals the square root of 2 times 882, well, we can say 882 times 2. And what is the square root of that, you ask? I don't know. Let's see. Square root equals 42. So if his new area was 882 inches And we use the formula to find what the new TV's size should be. It should be 42. All right, cool. Number two, Todd was driving. Oh, there's two more. Oh, okay. Todd was driving down Loop 1604 near 281 when traffic came to a complete stop. He quickly applied his brakes. How far would he have gone when applying his brakes if he was driving 65 miles per hour? Assume the pavement was dry and his brakes and tires were new. Use this formula where S is the initial speed in the miles per hour and D is the distance that the vehicle slides after the driver puts his foot on the brake. Support your answer with an algebraic problem and show your work. Okay. So he was driving 65. So that was his speed, S. And we want to know how far he, right? Where's the words? How far would Todd have gone when applying his brakes? So how much would he have slid afterwards? We're looking for D. So if S is his initial speed, 65, all we're doing is solving for D. So we'd first square both sides. 65 squared, well, let's see, 65 squared is 4225. Divide by 30, which is going to give us D equals 140.83. I guess it doesn't tell me how far, maybe miles? No, that's crazy. That's not right. I don't know what the measurement is. Maybe feet. Yeah, it doesn't list what type of distance. Okay. Well, that's how much he slid. All right, last one. Number 3. In 1985, the National Earth and Space Committee developed a formula that converts wind speed in knots to a comprehensible value on the Evers scale the committee can measure. The conversion formula is express wind speed s as a function of the Evers value. Okay, so this is just a fancy way of saying solve for s. All right, so we're going to take that formula and solve for s. 0.6 times 4. All right, so first things first, we should add 4 to the other side. E equals 6 times the square root of s plus 8.6. So we can divide by 6 on both sides. Now we have 6 equals the square root of s plus 8.6. Now in order to solve for s, we need to get rid of that square root. So we square both sides. Now, okay, I'm totally running out of space here, so sorry if you are too. All right, there's our answer. We now solved for s, or expressed the function as a value of s. Expressed wins, whatever. We solved for s, that's what we did. So that can go here. And how much speed is required to have an Evers value of 34? So we could plug 34 in for s, for e, sorry. So we have 34 plus 4 over 6 squared minus 8.6. Put that in your calculator. 38 divided by 6, square it. equals minus 8.6. All right, it's approximately 31.51, approximately. All right. Yeah, good luck. Ask me questions if you need help. All right.